Hi everyone, welcome to Paper 4 Theory Extended Igcse October November 2022 session. It's 1 hour 15 minutes, so we're going to have this video in two parts. So we're not going to be necessarily focusing on these questions, but if there's need to explain further on some of the concepts that might not be asked in this paper, we'll still explain. Okay, let's start. Number one, an aeroplane accelerates along a horizontal runway before take off. The aeroplane accelerates for 35 seconds. The speed of the aeroplane when it takes off is 72 meters per second. Fig 1.1 shows how the speed of the aeroplane varies between time t is equals to 0 and t is equals to 35 seconds. And the first question was saying define acceleration. Define acceleration. So basically, acceleration is the rate of change of velocity. Or you can simply say acceleration is equals to change in velocity over change in time. Okay, part B, calculate the average acceleration of the aeroplane between time t is equals to 0 and t is equals to 35 seconds. So what do we have here? We need to calculate the average acceleration. Average acceleration is equals to the average change in velocity over change in time. So in this case, we only have the final velocity is 72 meters per second, and I'm going to use 0 as the initial velocity, minus the final time, I have 35 seconds, minus 0, which is the initial time. If I divide the two, I'm going to get 2.0, 2.1 rather, 2.1 meters per second squared, or meters per second. Okay, let's go to part 3. Combined mass of an aeroplane, its passengers, and its fuel on takeoff is 1.1 times 10 to the power 5 kgs. Calculate the average resultant force on the aeroplane between t is equals to 0 and t is equals to 35 seconds. Okay, so we just want the average resultant force. So mainly in this case, we can apply the equation F is equals to ma. Force is equals to mass times acceleration. So we want the average, then the mass here is said to be 1.1 times 10 to the power 5 kgs multiplied by acceleration, which is 2.1. There we're given acceleration, which is 2.1. And the answer of the force is 230. 230 times 10 to the power 3 newtons. Okay, go to part 3. Force provided by the engines of the aeroplane is constant. Give one possible explanation for the change in acceleration of the aeroplane between 0 and 35 seconds. So one thing that may cause the change in acceleration there, if an aeroplane is flying, is the air resistance, because there's change in air resistance. So that's the only possible thing, air resistance. Okay. On part 4, on fig 1.2, sketch a graph to show how the acceleration of the aircraft varies between t is equals to 0 and t is equals to 35. So we can see from the graph above what is happening here, speed against the time, but we can see that acceleration is gradually decreasing. Acceleration is gradually It's gradually decreasing. Therefore, if acceleration is gradually decreasing, we can just show it here, showing that the acceleration is gradually decreasing as time is moving. Okay, so it is gradually decreasing as time is moving. So it's a curve. But this curve must not reach zero because we on the diagram above there, it's not being shown that the acceleration was zero, but it was approaching zero before. And also, we can note that okay, it was approaching zero, but just at 35, right? Okay, number two. Pic 2.1 shows a tennis ball approaching a tennis racket. The tennis ball hits the racket at a speed of 52 meters per second. The average force of the ball during the time that it is in contact with the racket is 350 newtons. The speed of the ball after it leaves the racket is 26 meters per second in the opposite direction to the initial speed of the ball. The mass of the ball is 58 grams. Now we are required in part one to calculate the change in momentum of the ball while it is in contact with the racket. Okay, so on this one, we know that the formula for change in momentum, remember, we say change in momentum is equals to final momentum minus initial momentum. Final momentum minus initial momentum. But we know that momentum basically is equals to mass times velocity. So in this case, if I'm coming here, final momentum is equals to mass times velocity minus initial momentum, which is mass times initial velocity. I'm using u there. Now, substituting the values that I have here, mass is constant because the mass is not changing. It remained as 58 grams, but it is very important to know that it is in grams. So I must change this 58 grams to kgs, and I'll get 0.058 kgs. Okay, now substituting into this equation, I now have 0.058 multiplied by the initial velocity. Sorry, the final velocity is 52 meters per second. Okay, we put bracket there. Minus, open the brackets. The mass again it's 0.058 multiplied by. Okay, something important there. Remember, we considered 52 meters to be the speed whilst it was going towards the racket, and that's a vector, so it is positive when it is going. But when now the velocity is going backward after hitting the racket, it now have a negative velocity. Remember of the direction. It is a momentum is a vector quantity. So it is very important to highlight there that the speed is now minus 26 meters per second. 26 meters per second. Now if we punch this carefully in the calculator, we we must get saying m 52. So it's going to be positive here because the negative and the negative, they need to add. Okay, I'm getting the change in momentum being equal to 4.5 kgs meters per second. Remember, momentum, we say that this goes to mass times velocity. So if we are to having, we call this a derived quantity where we are saying kgs in meters per second. So the unit is kg meters per second. Kgs meters per second. Okay. Let's go to the next question, part two. State an equation which defines impulse in terms of force and time. Okay. Before I state the equation there, it's very important to understand what is an impulse. The impulse is the period of contact between two bodies that are colliding. For example, if we think of cars that are hitting or that are having a head-on collision, that moment when they are stuck together, when they hit each other, is called the impulse time, right? So, because it's saying state an equation which defines the impulse in terms of time. Now, where does it come from? I would love to discuss a little bit on this one. We know that force is equals to mass times acceleration. At the same time, we know that force is equals to mass. But if I'm to substitute for acceleration, I know that acceleration is equals to change in v over change in t. Okay. Therefore, if I multiply by change in t both sides, I'm going to have change multiplied by change in t multiplied by change in t this side as well. It will cancel this side. So I'm going to have f multiplied by change in t is equals to m multiplied by change in v. So this ft is the impulse, which is the force times time, right? So we're saying impulse, rather it's ft is equals to m change in v. Maybe it's good if I show again that is the change in t. So this equation basically represents the impulse. It is the force times time as the impulse. Okay. Now calculate the time that the racket is in contact with the ball. So that impact we are talking about, there's certain time. How long does it take? Okay, when these two objects were together at that time when the ball hits the racket. So we call that impact time. So it is very easy from the formula that we have there. We know that impact is equals to we know that force times time is equals to mass times change in velocity. Therefore, we are supposed to make time subject to the formula. The change in t here is equals to m change in v over f. Okay, which is the force. So if I substitute there, remember I got the momentum, which is the mv here. Change in momentum was 4.5. So I'm going to say 4.5 divided by the force. The force I was given it. There it is. The force was said to be with the in contact with the racket is 350 newtons. So I would say 350 newtons. So if I divide the two, what am I getting here? I'm getting 0.013 seconds. That is if my calculator is telling yes, 0.013 seconds. Okay, let's move to the next question. Calculate the difference between the values of kinetic energy of the ball before and after impact. Before and after impact. Okay, one thing that you need to notice is that we know that energy is lost or energy is conserved. When energy is conserved, it means that there was no energy loss. All the energy was transferred. So let's just assume that there was conservation of energy. So if there was conservation of energy, if there was no energy lost, it means the kinetic energy before must be equal to the kinetic energy after. That is if the energy is conserved. So we want to see if the energy was conserved or if the energy was not conserved. So we know that kinetic energy is equals to half m u squared, which is before. Remember, we use the initial velocity must be equal to half m v squared, which is after. Now, if I substitute there, I'm going to have half. The mass, remember, I said it was 0.058 multiplied by the velocity. To know about sign because I'm going to square it, so that sign is still going to be. So before we had 52 being the speed squared there is equals to half. The mass is constant. Here the velocity, final velocity was 26 after it was being it was hit. It was 26 meters per second squared. Okay. So what is happening here? If I punch this in the calculator, I'm getting 78, 78.42. But now you can see that 78.42 is not equal to what I am was here. The answer is 19.6. 19.6 on the right side. So it's not true that the energy before was equal to the kinetic energy after. The kinetic energy before was equal to the kinetic energy after. Rather, the kinetic energy before was more than the kinetic energy after. So the difference in kinetic energy now becomes 78.42 that I got minus 19.6. And I'm getting something like 59 joules. That's the difference in kinetic energy. Okay, let's go to the next question. Fig 3.1 shows the cross section of a barrage built across a tidal bay. The barrage is part of a tidal power station. I hope we all know what's a tidal power station. A tidal power station, it is the one that uses the tides to produce electricity, and this has something to do with the moon. Remember, you did this space physics. You have to apply some knowledge in which you'll be explaining how the moon causes these tides. Anyway, let's focus on the question at hand. Shows the cross section area of a barrage. Okay, the gates are raised to be open when the tide comes in. The gates are lowered to close when it is high tide. Fig 3.1 shows the water level in open sea and the tidal bay when it is low tide. The gates are raised and water flow through the turbine. I think it is very important again to just for a minute just to explain the tide. What is a tide? So usually this happens in seas, in areas where there's a lot of water, in seas, in oceans. So tides, usually these are regular rise and fall of sea levels around the globe. It usually happens in the coastal areas where they experience too high and too low tides every day. I think you've come across such a scenario in seas whereby the levels they change every day. The levels they change every day. What is causing that? What is causing that? What is causing that? The moon, basically, because of time. I can't explain how the sun and the earth, but the influences these tides. But the major component that affects tides is the moon. The moon is the major component that affects the tides. Okay, complete the sentences to describe the energy transfers which take place when the gates are opened. Use the words from the list. Use the words from the list. Okay. All right. So from there, I can see that the gravitational potential. Let me just use GPE. Gravitational potential is this one of the. Of course, water is the one that will be possessing this gravitational potential energy. Okay. Gravitational potential energy of of the water in the tidal bay. In the tidal bay is transferred to kinetic energy, of course. Kinetic energy in the rotating turbines. Turbines are the ones that rotate turbines. Okay, so it's only a matter of time here. We're running against time, but I would want you to go and look more on these tides, on this tidal bay, right? How energy is produced from tides. Just go and check. You also need to understand how energy is produced from waves. I think it's a thing. I know most of you understand the thermal where we use core, solar, we use sun, hydro, where we use water, nuclear, where we use uranium in most cases, geothermal, You know all these, geothermal, what else, what else, what else, what else, what else? Wind. Okay. But now I want you to go and look more into these tidal, how these tides are used to produce electricity, and the waves, how the waves are used to produce electricity. It's a trick question. They might bring this, so you need to be aware as well. It's okay. State one advantage and one disadvantage of tidal power as an energy resource. Like we've just said that tidal power is an energy resource. We are using tides, and we want now to write just one advantage. However, there are many advantages that we can think of. Um, but one advantage, there's no pollution because we are using water. Sorry, no pollution. Another advantage, water is renewable. Water is renewable. Because we are using water. Water is renewable. You can think of another example, low cost as well. Low cost. Okay, then of course, disadvantage, since we are dealing with water, as long as we have iron there, there is increased rate of corrosion, increased rate of corrosion, increased rate of corrosion. You can corrosion. Okay, you can also high construction cost. Construction cost. It's very expensive to construct. Construction cost is high. They're actually more. State the main source of energy for tidal energy. Ah, okay. You remember I once mentioned about this, that the major or the main source of energy for tidal is the moon. However, the sun plays a role, the earth plays a role, but the main is the earth. Maybe to describe just a little bit how the moon affects, contribute in tidal energy. You know that if this is the earth, they say that this is the earth, and we are having the moon. Remember, the sun could cause this tidal, but the sun is far from earth. The sun is very far from earth, but the moon is a closer to the earth, and is the one that affect the earth more when it comes to the tidals. So what happens is this: we know that there is always the force of gravity, gravitational field strength that pulls everything towards itself. The same is happening with the moon. There is this gravitational field force. Okay, the moon is attracting the earth towards itself, and the earth is also attracting the moon towards itself. You know, the forces of attraction between two objects. So what is happening here is that because of fluidity, right? Because of fluids, because of they can flow. Fluids, you know that they flow. So what happens is that the water in the seas that will be in this side, is going to experience the force of attraction by the moon, and it will start to move upward due to this force of attraction, and this will cause the tides to rise because it has been attracted by the force due to the moon. And when these tides, this leads to the rise in tides. Okay, so usually in this here, due to the centrifugal force, there's also an increase in tides. So we call these regions on the top high tides, high tides, and here across there are the regions of low tides. Please just go and have a look again on tidal energy and see what happened exactly. Okay, let's move forward. Okay, there we have number four shows Fig 4.1 shows a liquid in glass thermometer labeled thermometer X. That's a liquid in glass thermometer. State the physical property which varies with temperature in a liquid glass thermometer. A physical property that varies. Okay, so we can talk about length here, length of the liquid That's the physical property. Length of length of the liquid. Right. It's the physical property that it varies with what? With temperature. Right. State thermometer Y has a bulb that contains twice the volume of liquid compared to thermometer X. State and explain how the sensitivity of thermometer Y compares with the sensitivity of thermometer X. So we are basically saying that okay, thermometer Y is a bulb that contains twice, that's the keyword, twice the volume of liquid compared to thermometer X. Okay. State and explain how the sensitivity of thermometer Y compares with the sensitivity of thermometer X. So we can see that Y is more sensitive compared to Y is more sensitive compared to X because it has more volume there. Okay. Okay. Or you can talk about more liquid will expand, which gives a larger change in the level of the liquid. Okay. More liquid will expand, giving a larger what? Change in the level of the liquid per degree per unit temperature. If I can write it like this, more liquid will expand, giving a larger per unit temperature. Okay. Let and explain one change that can be made to the design of a thermometer X to increase its range. Okay, we want to increase the range of thermometer X. So there are many designs that we can make so that the range increases. We can use longer capillary tube. We can use longer capillary capillary tube. So when you talk about the capillary tube, this is the capillary tube we are talking about, right? This is the tube side there. That's the capillary tube. So if it's longer, much easier. Okay. Explanation means that simply so that the liquid can expand further. So that the liquid can expand further. Okay. Is there another reason? Yes, of course. There's another reason that you can give there. You can talk of larger diameter. Yes, we can increase the diameter. We can increase the diameter of the capillary tube. Diameter of the capillary tube. And if we increase the diameter of the capillary tube, if we increase it means that we are going to lower the increase in level of each degree. We'll lower the increase in level of each degree because now we are saying that the capillary tube is more wider, meaning to say it is very sensitive to every degree. Meaning to say that it will lower the increase in level to the plates, right? Okay. A liquid in glass thermometer cannot measure a temperature of 1300 degrees. State a physical property which varies with temperature in the thermometer, which can measure the temperature of 1300 degrees Celsius. Okay, before you know, it is very important for you to know all the types of thermometers. Usually, we talk of this liquid in glass thermometer, the one that we have in this question, liquid in glass thermometer. We have the constant volume gas thermometer, constant volume gas thermometer. We also have the resistance wire thermometer, or we call it platinum resistance thermometer. Then we have the thermocouple thermometer. So you are expected to know all these four types of thermometers, and you must know their advantages, their disadvantages, where you should be able to know where to employ this or where to use this type of thermometer. You must know their properties, physical properties. You must know their thermometric properties. All that is required. So as you can see, a liquid in glass thermometer cannot measure the temperature. Why? Because this will best the liquid in glass thermometer will best if you put a temperature under, if you strain it under the temperature of about 1300 degrees, it will break. But in this case, the thermocouple thermometer, uh, this one can measure a high range of temperature. We know that it can measure a high range of temperature. So please go and make sure you are aware of all these type of thermometers, right? And all the information that surrounds them so that you'll be safe. State the physical property which varies with temperature in the thermometer, which can measure the temperature of. Okay, so the physical property, remember we said in the liquid glass thermometer it was length, right? That was the physical property. Then in platinum, it will be the resistance of wire. Resistance of resistance of wire. Then the physical property in the thermocouple thermometer is the EMF. We measure the EMF. So here you're supposed to put EMF, electromotive force. Electromotive force. Okay, number 5. The identical dishes A, B, and C contain equal volume of water. Dish A is outside in sunlight and experiences no wind during the day. Dish B is outside in sunlight and experiences a strong wind during the day. Dish C is in a dark room. Water evaporates from each dish. After 12 hours, the student measures the volume of water in each dish. Dish C contains the largest volume of water, and dish B contains the smallest volume of water. Explain in terms of particles why the three dishes have different volumes of water. So the key word is in terms of particles. You're supposed to explain in terms of particles. So you're being told that after and dish B contains the smallest, okay, because it was in the evening, right? It was dark in the evening. Then contains the largest volume of water, and dish B contains the smallest volume of water. Okay. So to explain this, I can say that the energy from the sun, right? Energy from sun is absorbed by water molecules. Is absorbed by water molecules, right? So kinetic energy of water molecules increases. And you know what happens once the particles kinetic energy increases? You know what that means. Molecules molecules with the higher kinetic energy escape from the surface. Molecules with higher will escape from the surface. Okay. Then that of wind, definitely wind remove molecules when they left the wind will remove quickly because it will be blowing. So wind will remove particles or molecules when they left the surface. And they leave the surface. Then of course we know that the wind increases rate of evaporation. Okay, so the keywords that were expected here is the kinetic. What happens to the molecules when they are heated? They definitely gain kinetic energy, and when they have kinetic energy, which means they can now escape from the surface, right? Due to the fact the intermolecular forces are easy to break because there's now movement. Then, because then if there is wind, wind will quickly take away those molecules that would have evaporated on the surface of the water. That's why it was left with the least volume. That's why it was left with the least volume in part B. Then of course wind decreases the rate of evaporation. Okay, specific define specific latent heat of specific latent heat of vaporization. Specific latent heat of vaporization is the amount of energy required to change 1 kg substance. Amount of energy required to change 1 kg substance from liquid to gas. From liquid to gas at a constant temperature. So this happens at a constant temperature. That's the key word there. At a constant temperature. That's very key. Okay. Let's see. Fixtures and insulating beaker, crushed ice, an immersion heater, and a thermometer. The initial temperature of the ice is minus 60 degrees. The immersion heater is switched on, and the temperature is recorded at equal intervals of time. Fig 5.2 shows the temperature time graph. Describe what occurs each in each of the sections A, B, C, and D. So it is very important to note that from this point is not zero. Most people they always confuse this as zero temperature. Then they put maybe this is 100 being the final temperature somewhere there, 100, right? But this is not zero. If we had to put the values here, let's say it's water, you would see that zero is here. That's where melting is taking place. So this is zero, right? This one is called the absolute zero. Absolute, absolute zero temperature. This one. Okay. Anyway, so what is happening from this absolute 0 point until it reaches 0 degrees with a certain time? Okay. So we can simply say as temperature increases, solid particles start to gain energy and vibrate. Right? So as temperature increases, solid particles start to gain energy. Okay. Right. At B, melting is taking place. At B, remember, melting takes place at a constant temperature. Melting taking place. Right? Melting at a constant temperature with time. Remember, time doesn't stop. Okay. Then on part C, what is happening? We're saying that that's the liquid now. Now you have the liquid, or we can say liquid gaining more energy. It's the liquid that is gaining more energy, gaining more, gaining more energy with time. With time, right? Okay. Then part D, particles are converted to gas at a constant temperature. So boiling starts here, right? This is where there is boiling, right? So this is where there is conversion from liquid to gas. Say that liquid to gas at a constant temperature. At a constant temperature. Okay. All right. So for number six, fig 6.1 shows wave crests and the direction of travel of a water wave approaching a barrier in a ripple tank. Okay, that's a ripple tank, large area ripple tank direction of travel. The wavelength of the wave is 1.6 centimeters. Draw on fig 6.1. Draw the direction of travel of the travel of the reflected wave. Okay, so let's go there and try to draw the travel of the reflected wave. Right. So don't confuse yourself too much when it comes to this one. Just consider this arrow. This arrow is very important. I know you know that you are used to this situation whereby you have the boundary when there's reflection, where a light would come, then you'd call this a normal, a line that is there, and to be reflected. Sorry, this is showing the arrow, then it will be reflected away from the boundary like this. We would call this angle of incident and angle of reflection. So so don't stress yourself too much. Just consider this line, right? You know what's going to happen? It's going to be okay. It's going to show some that's a reflection. But now in terms of reflection, the lines that we have or the wave crests, they are now perpendicular to these ones. They are like this. Remember, they should be the same wavelength. They're equal. Okay, something like this. They appear to be. They are showing that they are perpendicular to those ones. Is that clear? Okay. So then the next one is saying three successive. Okay, so you're supposed to draw three successive reflected wave crests. So these are the three successive reflected wave crests. These ones, right? One, two, three, right? The arrow showing that it's going in that direction. Okay, let's go to the next question. Fig 6.2 shows an identical wave approaching a barrier with a gap of 1.3 centimeters. On draw three successive wave crests after they are after they pass through the gap in the barrier. Okay, so these wave crests, be very careful of drawing straight lines. If they are passing through this gap, they become curved. So don't ever draw straight lines like this. Rather, you draw the curve. It becomes like this with the same wavelength there. Oh, something like that. Okay, let's ignore. So we're just assuming that the distance is the same. It should be almost the same distance as that one. From grave to grave should be of almost the same. Okay, so we've drawn that right now. The frequency of the wave, the frequency of the wave is 4 hertz. Calculate the frequency of the wave. We know that the formula for calculating the frequency of the wave, its velocity is equals to f lambda, frequency times lambda. Okay, so we were given the velocity Calculate the speed of the wave. Okay, one the speed. So the frequency is 4, and I think the velocity is given. We check. Sorry, the wavelength was said to be wavelength. The wavelength is said to be 1.6 centimeters. The wavelength is said to be 1.6 centimeters. So we can calculate using 1.6 centimeters. But don't forget to convert centimeters to meters. That's 1.6 times 10 to the power negative 2 meters. And if I punch this in the calculator, I'm getting 0.064. Remember, speed is measured in meters per second. Okay, that being done, let's don't forget to subscribe so that the next video can pop up on your screen. So we finish from number 7 to number